In this video, we're going to go over solving equations, more specifically solving linear equations in one variable, or what some people call basic equations. But before we get into actual techniques for solving, I want to talk about kind of what an equal sign is. I think that's not something that's always clearly understood. And also just the nature of the strategy for solving equations. So let's just say we have a simple statement like 8 equals 8, and that's just saying that the left side is equivalent to the right side. Now, if I wanted to, I could adjust the left side by adding 2 to it. And then to maintain the statement of equality, I would have to add 2 to the right side as well. And that gets into the strategy that we'll use for solving equations, that we start with a statement of equality. It doesn't matter that these are 8s. Or when we get into the more complicated algebraic statements, it's not the statement that matters. I mean, the statement matters a bit, but our process for doing it is based on the fact that it's an equal sign. It's the equal sign that drives the entire strategy of this idea that the left side is exactly the same as the right side. And that's an assumption we're making from the beginning, and everything we do is to preserve that assumption. Now, it's possible that we have this statement 9 equals 8. And then if we do everything we can to preserve that assumption by always doing the same thing to both sides of the equation, the fact that it's wrong stays wrong. So even if it's not equal, if we do everything we can to preserve the assumption that it is equal, we can actually, in the end, reveal the fact that it was a false assumption from the beginning. So anyways, everything we're going to be doing hinges on this fact of assuming that the left side is equal to the right side, and we do everything in our power to maintain that equality. Now let's consider the equation x plus 3 equals 8. Well, here the x is what we call the unknown. And so the question is what value does x need to be for this equation to be true? And I wrote a simple one so that we could see just by inspection that x needs to be equal to 8. If x were 8, then this would be a true statement. Now, the reason why I'm introducing this idea is because this gets at what we call the solution to an equation. A lot of times when people are learning math, they talk about the solution and the answer to any problem is the same thing. But the solution to an equation, or the word solution, is preserved to the idea that it's going to be whatever value you plug into a variable in an equation to make it true. So again, the solution to an equation is the value for the variable that makes the equation a true statement. Now, I made the option in there for it to be plural because it is possible that you have more than one value that works in the equation. And it's also, we'll be eventually working with equations that have more than one variable. But the idea of a solution remains the same. It's those values that can go in for the variable that make it a true statement. So in this equation, x plus 3 equal to 8, our solution is 5, because 5 is what we can plug in for the variable that will make that a true statement, since 5 plus 3 equals 8. So now I'm going to do this using solving techniques that we use in general with solving equations. And our general strategy with solving equations is you can do whatever you want as long as you preserve the idea of equality. In other words, you can do whatever you want as long as you do the same thing to both sides. You're going to keep the equation in balance. Now in this case, we're working with one, like I said, I chose it because you can just know by inspection that x needs to be 5, but we're starting with a simple one so you can see how the properties of equality work. So in this case, what I'm going to do is I'm going to essentially, we call this getting x by itself. So right now on the left side, there's this plus 3 with x. And if I can get x by itself, then I'll know what x equals. So what I want to do is eliminate that plus 3. Well, the way I can eliminate the addition of 3 is to do the opposite and subtract 3. So if I subtract 3 from that plus 3 on the left, it'll eliminate itself. But my properties of equality say that whatever I do on one side, I have to do on the other side to preserve the equality. Now just simplifying this gives me that x equals to 5. And so that gives us the idea that a lot of times people think that this is the solution, and that's not really the solution, that's just an equation that makes the solution very overt. The idea here with this equation is if I plug a 5 in for x, then I'll have 5 equals 5, which is a true statement. The solution is 5. It's the value for the variable that makes the equation true. It is not itself an equation. So the solution there is 5. But really what I'm wanting you to see there, since we already knew the solution was 5, is how we can use this idea of what I call undoing what's happening to x in order to determine what value we can plug in for it to make it true. On this one, we started with something that we could see from the beginning, but we'll have more complicated examples where it's not as easy to see it with inspection. And when you can see it with inspection, it's really unnecessary to go through this step. If you can just see something, just say what it is. But this, I'm starting with these so you can kind of see how it's working for when we get to more complicated problems. Alright, so now let's look at this equation, 2x equal to 10. And remember, when a 2 and an x are glued together, that means times. So this is saying 2 times what number will give us 10. And again, I chose one that hopefully you can see by inspection. X is going to be 5. But I still want to work with this idea of canceling out what's happening to x in order to get x by itself so we can see explicitly what x equals. So in this case, what's happening to x is it's being multiplied by 2. The opposite of multiplication is division, so we're going to divide that by 2. And we're allowed to do that so long as we also mimic it on the other side of the equation. Now actually doing the math here gives us that x equals to 5. Again, that's not the solution, that's just an equation that makes the solution very obvious. If I plug a 5 in for x, then I'll have a balanced equation, which means my solution is 5. Alright, so that's a couple of examples where you can see what's happening without going through the more sophisticated strategy of undoing what's happening for x. We'll do one more like this, and then we'll start mixing it together where you can't just see from the beginning what the solution is. Alright, so let's say we have this, x over 6 equal to 2, and that over is division, so what number divided by 6 gives us 2? This one may be harder for people to just see what it is because division is more challenging for our brains. But hopefully you can still see that the idea is that x is 12. If we take 12 divided by 6, we're going to have a 2 as a result. But to see how our properties of equality work, again, I can do anything I want as long as I maintain the equality. Well, right now x is being divided by 6. The opposite of that would be to multiply by 6. And I like to put it as 6 over 1 since we're dealing with fractions, just to emphasize this is a 6 in the numerator. And then we can do that so long as we also multiply by 6 on this side. On the left side, they end up canceling out, which is the whole idea of these. What we're choosing is to choose numbers that cancels out the number that's hanging out with x. So that's going to give us x equal to 12, which tells us our solution is a 12. So when we're solving equations, we're essentially undoing what's happening with x. So we're going to switch to equations where multiple things are happening with x. So we can practice undoing things to see the real benefit of these properties of equality when we're not working with equations where we can just see where we're going from the beginning. Alright, so let's say we have 2x plus 3 equal to 7. And maybe you can see from the beginning what x is, but I promise you we'll get to ones that are more complicated. We're just working up to them. So here we want to undo what's happening to x on the left side of the equation. Right now x is being multiplied by 2, and then we're adding 3 to it. And this is sometimes confusing to people, because what we're going to do as we undo what's happening to x is we're going to do the opposite for the 3, so we're going to subtract 3 from both sides of the equation. Then we'll do the opposite for the 2, which means we'll divide both sides of the equation by 2. The reason why that can be somewhat confusing is if you're leaning on your order of operations says to multiply first and then add. And we're essentially doing it in the exact opposite order. But keep in mind, we are undoing what's happening to x. So when you undo things, you do them in the opposite order that they would have occurred going in forward. So that's the reason why everything's going to be the opposite of what we would do if we were actually doing this math. In other words, if I had a number that I plugged in for x, I would multiply by 2 and then I would add 3 to it. But that's not what I'm doing. I'm undoing that. So I'm going to start by subtracting 3, and what I do on that side I need to do on this side over here. Simplifying that down gives me 2x equal to a 4. Now I need to take and divide by 2 to cancel out the multiplication of 2. So the result of that is that x equals to 2, which means my solution is a 2. Now some of you might have saw that from the beginning, but that kind of gives you the idea of how we can compound these properties of equality into multiple steps to unravel what's happening to x. Let's make it a little bit more complicated. Alright, let's say we have negative 3x plus 4 equal to 7x minus 5. So it's getting more complicated to sit there and just mentally plug numbers in for x and see what works. So this is where our strategies for solving really start getting beneficial. Now in this case, the complexity we've added here is that we now have x's on both sides of the equation, and our strategy is to undo what's happening to x. Well, if we have x's, what we want to do to employ our strategy is first get it so we only have an x, so that we can then undo what's happening to that x. So what I do with that is I essentially want to kill off one of the x terms, either on the left or right. I habitually, if I have a choice on the left or right, I will habitually eliminate the x term on the right side of the equation, or on the right side of the equal sign. So if I have a 7x on the right side of the equal sign, the way I can eliminate that is by subtracting 7x, because 7x minus 7x is 0, therefore it's eliminated. Still have my minus 5 in there. Now, so I've done what I wanted to do on the right side, but I have to also do it over here on the left side. And remember, I'm subtracting 7x, so if I throw it out there in front, it's a negative 7x. So doing the simplification on that gives me a minus 10x plus 4 equals to a minus 5. At this point, we've essentially gotten it back to the type of problem that the previous example was. So there's a number of x's being multiplied and then we're adding. So we need to undo that by first subtracting 4 from both sides and then dividing both sides by a negative 10. So I'm going to subtract 4 to cancel out my 4, but what I do on one side I have to do on the other side. So I get a negative 10x equal to a negative 9. And now I'll divide both sides by my negative 10. Negative divided by negative is a positive, so we get x equal to 9/10. And I like those to just stay as fractions, unless there's some argument for making it a decimal, such as like we're dealing with money and we deal with money in decimals. But this tells us that our solution is 9/10. Which means if I plug 9/10 into my two x's I had originally, then this would make two numbers that are equal on each side of the equal sign. So we're going to continue to add complexity to this, and as we do, if you need to spend more time with any particular example to see what happened, you can always just back it up and watch it again before going on to the next example. But we'll add some complexity in the next example. Alright, this example definitely has more complexity on both sides of the equation and is definitely going to need our properties for solving equations, our properties of equality for solving equations. I, for one, can't just look at this equation and tell you what the solution will be. So how this one got more complex since the last one is if you look at one side of the equation, there are things we could do to simplify that side of the equation. Same thing with the right side of the equation. We could distribute things, and after distributing we can collect like terms. And so when you have this situation, that's exactly what you want to do. You want to simplify each side of the equation as much as you can, and then once you get each side simplified, you would start using our solving techniques that we've been talking about. When we're simplifying, we are doing the math that actually is there to do. So for example, I'm going to distribute this 4 by multiplying. That's what is there, and that's what I'm going to do. The reason why I emphasize that is because when we're solving, we're undoing what's happening. So first, for this more complex example, we're going to simplify each side by doing the math that's there. And then once we get each side as simple as possible, then we'll start through our solving techniques of undoing what is on each side of the equation. So like I said, I'm going to start by distributing the 4. That would give me a 4x minus 20. And I also brought down the -3. Didn't change, I just brought it down. And then on the right side here, I treat that minus that's outside the parentheses like it's a -1, and I just distribute the negative in the parentheses. Switches the signs of everything that's in the parentheses. And then that's what I get there. Now notice, I brought down everything whether it changed or not, and this is a good habit to get into. Sometimes people will only write down what changed, and I've just seen that cause all kinds of error, not because someone didn't know what they were doing, just because they kind of lost track of something. So I encourage you to get into the good habit of when you do these problems, you write down everything in the next step. So what I mean is this line right here has everything in the problem that I need. I don't need to look back to this line to continue to work it. I just work off of the line I'm now on. And this, doing that, taking the couple seconds, maybe not even that, it takes to copy down what didn't change, can save a lot of those simple errors that drive us nuts. Okay, so the next step, like I already alluded to, we're going to combine like terms. So here on the left side, I can combine the -3 minus the 20. On the right side, I can go ahead and do the 2x minus x. And then I can also combine the constants on this side. The -2 plus 3. So we're still in that phase where we're doing what's happening. So I'm going to go ahead and combine all those like terms. So I just habitually always put the x term first. So I'm going to bring down the 4x, and then I would have a minus 23 on the left side. You could have written a minus 23 plus 4x. That is the exact same thing and completely okay. I just have developed the habit of always putting my x term first. So on the right, when I combine like terms, I'm going to get an x plus 1. Alright, at this point, step back and look. On each side of the equation, there's nothing more we can do to simplify that side. And that's the point when you want to change gears and start doing the solving techniques that we've been talking about. So instead of doing the math, we're going to start undoing the math. And this one, like the previous example, has an x on both sides. So I'm going to go ahead and eliminate the x on the right side. And I would do that by subtracting x, because that would add to 0 and bring down my 1. It's not going to change. But whatever I do to one side, I have to do to the other side. So I wrote in what I was doing. Now I'm going to go ahead and do it. So this would give me 3x minus 23 equal to my 1. Now that I have it so there's just one x term in the problem, I'm going to undo that. And so right now what's happening to that x is it's being multiplied by 3 and then subtracting 23. So I'm going to add 23 and then divide by 3. So we would have 3x minus 23 plus 23. That's going to equal 1 plus 23. So simplifying that, I'm left with just the 3x on the left and a 24 on the right. I'm going to bring this up here for the sake of space. So now to undo that 3x, that's 3 times x, so the opposite of that times is division. But what I do on one side, I'm going to have to duplicate on the other side. Alright, so now when I actually do that division on the left side, it will cancel out, or it reduces to a 1 is what really happens. So we have a 1x. And then over here on the right, we have an 8. And that tells us that our solution is an 8, meaning I can substitute that 8 in for x and it produces a true statement. Now, granted, I could do it there in that last line, but we really can do it in any line along the way, and the one we're really concerned about is the original equation. So if I take this original equation and substitute an 8 in for each one of those x's, if it is the solution, it'll produce a true statement, and that's a good way to check to make sure you've done your work correctly. In this case, you should end up with the statement 9 equals 9. I encourage you to go ahead and pause the video and give that a run through, just so you can see how that works, and then you'll know that anytime you come up with a solution, you can always plug it back into that original equation, and as long as you plug it in correctly and compute it out correctly, then you can verify whether or not it is a correct solution. Okay, there's one more complexity I want to hit on right here at the end, and it involves division. This is a little scarier for people, but it's still the same strategy that we're going to be undoing what's happening to the x. It's just kind of complicated what's happening to the x once we start throwing division in there, or fractions. Fractions are just division. So what we saw in the third example was we undid the division by multiplying. So right here it's more than an x, it's an x plus 3, but it's being divided by this 4. And we can undo that division by multiplying by 4. And we could do that right away and that would be fine. But I'm going to show you kind of a little nuance that's kind of fun and gets at some of the strategies we can do in mathematics to add to our efficiency. Over here, 2x minus 1 is being divided by 6. And I could clear out that division by multiplying by 6. So one step would be multiplying everything through by 4, and another step would be multiplying everything by 6 if we just applied our strategies like we have been doing. But there's this little thing we can do that's kind of, again, like I said, makes it more efficient. There's a number that contains both a 6 and a 4. Well, there's lots of numbers that contain both a 6 and a 4, but we can choose the smallest one for the sake of efficiency, and that's a 12. A 12, there's a 6 inside of that, and there's a 4 inside of that as well. So does 24, or, you know, we could go up from there. But 12 is the smallest guy that contains both a 6 and a 4. Now keep in mind, if I multiplied through by 4, and I multiplied through by 6 separately, that would be the same as multiplying through by 24. Which would get the job done, it's just using a bigger number, so it's going to inflate everything more than what's necessary. So it's just more efficient if I multiply through by this 12, and it takes care of the 4 and the 6 all in one step. This 12 is what's called the least common multiple, or least common denominator, of 4 and 6. So that's kind of the target number that you're aiming for. It's the same number you would aim for if you were getting a common denominator. So if I take and multiply both sides of my equation by that 12, I'll cancel out this division. So I went ahead and wrote what I inserted into the equation on both sides. in red just for the sake of contrast, because this is a little bit more complex of a situation. The right is simpler in a sense. The right side has less going on, and so I'll work with it first, and then we'll talk about the left side. So the idea there is that we're going to take the 12 divided by 6. Well, 12 divided by 6 is a 2, so I'm just going to cancel that off or reduce this to a 2. And then when I bring that down here, I'm going to write it as 2 times 2x minus 1, because we'll need to distribute that 2 in the next step, but we'll just do the reduction in this step. So that's what that looks like. The reason why the left side is more complicated is because it has two separate terms. It has the fraction we're trying to deal with, and it also has this minus 5. And even though the minus 5 doesn't need a denominator canceled off of it, it still needs to be multiplied by the 12, because that's our property of equality in play, that we have to distribute everything out equally to maintain the equal sign. So I'm going to have to distribute this multiplication to both of these guys. When I do that, I'm going to keep my 12 in red so you can see what's going on. And then this is going to be an x plus 3 over 4. But then with the 5, I can just go ahead and do the math on that. 12 times 5 is 60, and so I can just write a minus 60 there and call that one done. Hopefully you can see what I'm doing there. The reason why I didn't do the math with the 12 is because it's a reduction step, and I just wanted to be able to show you what's happening. I'm doing 12 divided by 4, which is a 3. And then what I have there is 3 times x plus 3, bring down my minus 60, equals 2 times 2x minus 1. Now, take a step back, make sure you understand all that. From this point forward, it's like solving some of the other equations we've solved. And I'll go through that, but this new stuff with getting rid of those denominators by multiplying by a common multiple for efficiency's sake is kind of tricky. There's a lot of details to it, so if you want to back up and go back through that all, you can. And I would encourage you to break that down into as many steps as you need. As you get more comfortable with what's happening, you might be able to glaze over and writing all this out into 3 separate steps. You might be able to do it more at once, but I would just encourage you to break it down into steps, because a lot of times if you try to do it all in one fell swoop, you'll lose one of the details, because there are a lot of details here. But what I'm going to do now as I move forward is I'm going to erase this stuff and just move my bottom equation here up to give me some room for solving it. Now, like I said, once we've gotten rid of those fractions, we're back to solving something like we've worked with before. So I need to simplify what's happening on the left, and I need to simplify what's happening on the right. That starts by distributing this 3. I'll just bring down my minus 60. And on my right, I'll distribute the 2. And then on the left, I can combine the 9 and minus 60. So I have 3x minus 51, and just bring down my right side. So again, I want to emphasize that you notice that every time I'm bringing down the complete equation, whether it's changing or not, if it doesn't change, I just copy it down. It's a really great habit to get into. Alright, so now that I have the left side and the right side simplified independently, I'm going to get it so that I only have x's on one side of the equation. I'm going to do that by eliminating my 4x on the right by inserting a minus 4x, because those add to 0. What I do over there, I'm going to have to do over here on the left. Okay, so I get a minus x minus, oh, that should be a 51. I'm glad I caught that. Equal to a minus 2. Now, to get x by itself, we're going to undo what's happening to it. So it's being subtracted by 51, so we're going to add that 51. Why do I want to turn that into a 50? I'll write the result up here. So we get a minus x equal to a 49. Now, you can think of this a few different ways. I tend to think of it as x is being multiplied by a -1, so I'm going to divide both sides by a -1 to cancel that out. This is how I routinely think about it. I don't always necessarily show the steps, but it's how I think about it. And that gives us x equal to a -49. You could also just multiply through by a -1. That would flip the signs of everything. That's less in vein with the strategy we've been following all along. Another way to think about it is if the opposite of x equals 49, then x equals -49. And just think about it in terms of the idea of opposites. So it doesn't matter. All the same, you'll get the that the solution is -49. All of those are fine logical ways to think through it. The reason why I stick with dividing by the -1 is because that's still in vein with our strategy of undoing what's happening to the x. So there you have it. This is a fairly complicated example of an equation. Dig into some practice problems. Start with the simpler ones. Even if you can see what x is going, what you're going to determine x is going to be, starting with those simpler ones helps you give yourself some training on the pattern of getting into the habit of what to do, so that when you get more complicated ones, you don't get lost in the detail, and the habit of what to do has already been trained on the simpler ones is the idea. So go ahead and give some of these a try and see how you fare.